Now, how do we think about comparing algorithms? If I have two algorithms to solve the same problem, which one is better? Well, this is where the idea of complexity comes in. So complexity refers to how we measure programming efficiency in an objective way. And we actually need to think about this a lot, especially in industry, because you want to be able to predict for some algorithm that you've come up with, how will it handle a given input size? Like if you think back to Lab 7, where you did the dictionary, where you were using dictionaries to analyze Shakespeare and other writers, you want to be able to reason about how well your algorithm would do if you gave it all of Wikipedia, or if you gave it all of the Harry Potter books. You also want to be able to compare and pick a best algorithm if you have a couple. And so for that, we need some objective way to think about how fast a program runs, or a particular algorithm, how efficient that algorithm is. So I slipped up and said the word fast, but we should be clear here. Efficiency can mean multiple things. And in programming, we think about two main types of efficiency. We think about time efficiency, which is how fast a program is. So how quickly does it give me an answer? And we also think about space efficiency, which is about how much space a program uses in memory. And generally when people talk about these, and what you'll hear in interviews is they'll ask you for the time complexity or the space complexity of a solution. And by the end of next lecture, we'll work your way up to giving an answer in an interview on what the time complexity of your solution is, or the space complexity. But today we'll focus on just time complexity. And actually, we'll even limit our scope a little bit more for today. There's a few different ways we can think about runtime. The first is really interesting. We can just measure the length of our program with a timer, like a stopwatch. We could also count the number of operations, or we can think about order of growth. And order of growth we will get to in our next lecture. But today we'll talk about measuring with a timer and counting number of operations. So measuring time with a timer. Actually not that hard. Python has a time a time module built in, and you can just get that time module. Then you've defined your function. You can grab the time right before you call your function. You can call your function, which has the algorithm in it, and then you could stop your clock right after. So you effectively get the time after. And then when you do subtract the time after minus the time before, you get the difference. And this function, time.time_ns, gives you the current time in nanoseconds. And so by looking at the difference, you can find out how many nanoseconds your program took to run. So let's take a look at this in Replit. I've gone ahead and copied that same code over. And this function here is Celsius to Fahrenheit. So Celsius to Fahrenheit, this is actually the equation. Do you have a prediction on how fast this will be, or how slow? How long do you think it takes Python to convert, like given Celsius, multiply by 9, divide by 5, and add 32? Take a guess. How many seconds? Actually, I'll give you a hint. It'll be definitely 0 seconds. It'll be less than a second. Try to take a guess how many tenths of a second, or how many hundredths of a second. Well, let's run it and find out. So main.py. Okay. So our program took 3,783 nanoseconds. So that's actually less than even 1/10 of a millisecond. There are a million nanoseconds in a millisecond. So actually, nano prefix, let's even look it up. Yeah, wow. So 10 to the 9. Yeah, so running this one operation, these three operations here, multiply by 9, divide by 5, add 32, took less than 1/10 of a millisecond. It's crazy. So how long now, if we want to try seeing how this number changes. How long would it take, do you think, if we did this maybe 1,000 times? For I in range 1,000, we're going to call our function cells to Fahrenheit. Whoops. So actually, let's run this once before as it just was on its own. This time 2,523 milliseconds. And by the way, I'll just point out, notice if I run this a few times, it varies a little bit how long it takes. 3,000, 3,500. Because at any given time, the computer where this is running is doing some amount of work, and it might be busy. Some of its resources might be used, but it's around the same amount. So now if I do this 1,000 times, we should expect the program to take longer to finish. And in fact, it does. You can see it takes now 0.3 milliseconds. What's kind of interesting is I'm doing this 1,000 times. Notice that it's not 1,000 times bigger. It's some smaller amount. It is much bigger. It's about 100 times bigger. But that's because if you call the same function multiple times, Python actually has a smart way built in where it can figure out how to optimize that and do that in a more efficient way. So it doesn't make it a full 1,000 times slower, but it is much slower. Now it's a whole 0.3 milliseconds. And you can do this with a whole bunch of programs. Like, what if you wanted to write a different function that goes through and copies a list? Like, have you ever wondered how long does it actually take to copy a list? So if I start with a list, let's say that we have a list that has for I in range 100. I'm going to make a list that has 100 items. And now I just want to measure how long does it take to make a copy. Duplicate equals copy.deepCopy items. How long does that take? So actually, making a copy of 100 items takes 0.15 milliseconds. And let's see how that changes. Let's say I want to make 1,000. So, well, actually, yeah, 1,000. So a factor of 10 bigger with 1,000 items. It's actually much slower. Like, look at that. By a large factor slower. We don't have time now to talk about why it's so much slower. Why is it not just 10 times slower? Here it's actually 100 times slower. But you'll learn about that in future classes. But just notice how when I make the problem harder, I make our numbers bigger, the program will take longer and longer to run. So now it took a whole 45 milliseconds. Still blazing fast, but slower. So this is the time module you can use to time how long your code runs. Well, let's think back to our tourist problem. What about here? How would we measure how efficient our algorithm was, the solution our algorithm came up with? Like, we could use a stopwatch, and you could time yourself starting from Logan's Circle, walking all the way to 16th, and walking down for the solution. But if we want to compare our algorithms, how do we figure out which one's better? One option that you could do is you could take a race. You could have a race with your friend. So you and your friend both time yourselves walking, starting from the same place. Y'all are right at Logan Circle. And then you take one path, your friend takes another path, and you time yourselves to see who gets to the White House first and how big of a difference there is. Can you think of anything wrong with this approach? Well, one problem that I see is, what if you and your friend don't walk at the same pace? Maybe your friend is a much faster walker. Or what if your friend actually has a scooter? And I know that, or you get tired more easily. I know that scooter example seems silly, but this is really similar to how computers work. And a computer could have a faster processor. One computer could have a limit on how much power it can, it can pull from out of the socket. One computer might have less memory. And so we have this problem. Our goal was to evaluate different algorithms. And looking at running time does, we do notice a variation between different algorithms. But with different implementations, like if you're on a scooter or you're walking the same path, the time actually varies, and that's not ideal. It also varies between computers. In fact, it's not very predictable. Like you saw when I just ran, what I just ran, the numbers kind of varied from run to run. And it certainly varies for different inputs. It's hard to express a explicit relationship between a given input and a time. Can we do better?